Hey everybody, this is Scott Grammer and I am the Old Audio Guy, and welcome to part 2 of the Cheap Chinese Amplifier Refit, or CCAR as I'm calling it now. So I've done some pencil whipping on schematics for how I think I'm going to rebuild this thing, and I want to share some of those with you right now. These are subject to change. Basically everything that can be done in an analog vacuum tube audio amp has already been done. Most of this stuff was invented in the 20s and 30s, and it has been done every way that can be possibly done. None of this that you're about to see is original. I did not invent any of this, and I'm not saying that I did. So in case anybody has any questions about, oh, did you come up with that? No, I just borrowed other people's work and tweaked it the way I want it to be. First, I want to show you the original schematic for the amplifier. This is for the amplifier circuit itself. They've got a 6SN7 and then the EL34. The two halves of the 6SN7 are wired in parallel to be treated as a single triode. And this is a fairly common approach, and they do it to reduce the plate impedance of the triode in order to provide it with a little more current capability, a little bit more drive, a lower source impedance, in other words, to drive the EL34. But I have a better idea, I think, and I'll show you that in my proposed drive circuit. As you can see in the upper right-hand corner of this schematic, I have made a note that the suppressor grid of the output tube was not connected to anything, and that is a very bad idea because an unconnected grid will develop a space charge around it of whatever voltage the tube feels like creating, and this can cause very unpredictable operation of the tube. There's no way to guarantee that it's not going to cause distortion, essentially. In fact, it pretty much guarantees that it will cause distortion. So what is normally done is the suppressor grid is tied to the cathode. That's how it's usually done, and that's how I've done it in my new schematic, which you'll see in a minute. This is the old power supply, and the first thing I want to note is there are no bleeder resistors in this power supply. The only thing that will cause the capacitors to discharge after you turn off the power is for the capacitors to discharge through the tubes. Now, if you happen to have the tubes unplugged with it turned on, or if the tubes are not fully warmed up and the power supply voltage is up, the filter capacitors will not fully drain. And this is dangerous because you could end up getting yourself bit. So any proper power supply is going to have some form of bleeder resistors, and my new power supply does, which, again, you'll see in a few minutes. The other thing I want to point out about this old power supply is how much voltage is being lost through the 5U4 rectifier tube. They're losing a lot of voltage through that tube, and that's a lot of output power that you could have had from your amplifier if you had not lost it in that vacuum tube rectifier. Again, this is something that will be addressed in my new power supply. Finally, the power switch in the original power supply does not have any sort of snubber capacitor across it. Now, the purpose of a snubber capacitor is this. When you turn the power off to a power transformer, the magnetic field that's stored in the transformer will dissipate very quickly. It will collapse, and this creates a very high voltage spike across the primary of the transformer, and this arcs across the power switch at the moment that you turn off the power, and this causes two problems. First of all, it can cause a pop through the speakers, and second, it's very hard on the switch. It will cause the switch to wear out and fail. And so a snubber capacitor is normally put across the power switch to absorb this high voltage peak. And I will be putting one in. In fact, I've already got it put in. You'll see a picture of it in a few minutes. So here is the new driver circuit that I have proposed. This is 2 stages. The first stage is a single 6SN7 triode as a voltage amplifier. It has an unbypassed cathode resistor, which means I'm deliberately throwing away a little bit of gain. That unbypassed cathode resistor acts as local negative feedback, reducing the gain of that amplifier stage and reducing its distortion and noise as well. So the input signal goes straight into the tube. It does not go through the volume control first. This has a good and a bad effect. The good effect is that it improves the signal-to-noise ratio of the amplifier because as you reduce the volume control setting on the amp, you're reducing whatever noise this stage creates. The downside is that there's a limit to how much input voltage you can feed into this stage before it distorts, and there's no volume control to stop that. But With proper design, this input voltage limit will be far above anything that you're normally going to encounter. It's going to be several volts, and you won't normally be driving that much out of your preamplifier or whatever other source you're driving into the amplifier. So after the volume control comes a pair of 6SN7 stages, one atop the other, and this creates what's called an SEPP or SRPP, depending upon who you ask, circuit. SEPP is the name that I usually refer to it as, meaning single-ended push-pull. What it amounts to is the bottom tube is a normal triode voltage amplifier stage, but instead of having just a resistor to feed the plate, the top tube acts as a constant current source. Using a constant current source in place of that resistor reduces the distortion considerably and also provides a lower source impedance with which to drive the output tube. And this is a good thing because I want to be able to drive the grid of the 6L6 positive a little bit. I want to be able to push it into positive territory, and the reason for that is it gives you much more output. Being able to drive the grid positive can give you considerably more output power than a driver stage that can only drive the grid up to the 0 volt point, and then it runs out of steam and stops because the grid begins to draw current. So by the way, if you've ever heard of Class A1 and Class A2, or in the case of a push-pull amp, Class AB1 and Class AB2, the 1 and 2 refer to the fact that in a Class AB1 or Class A amplifier, there is never any grid current drawn by the output tubes. The grids are never driven positive, whereas in a Class A2 or Class AB2 amplifier, they are driven positive. So this will be a Class A2 amplifier with any luck. This is the new power supply section, which again is tentative, subject to change. The biggest difference is that it uses solid-state rectification, a full-wave bridge rectifier made up of 8 1N4007 diodes, and 8 1 megohm resistors. Now these resistors across the diodes do two things. One, they equalize the inverse voltage across the diodes when the diodes are not conducting, and two, they act as bleeder resistors for the filter capacitors. Then the filter capacitors are much larger than what was in there before. These are 550 volt filter caps. The originals were 450. The reason I'm doing this is that the solid-state diodes do not throw away the kind of voltage that the 5U4 vacuum tube rectifier did, and so our B plus is going to be about 100 volts higher. It's going to be around 450 volts, and I don't want to run 450 volts on 450 volt caps. I don't want to run them right at their limit, so these are some new electrolytics that have just come out, 550 volt capacitors, and that way we'll have a little bit of headroom for the voltage rating of the caps. The bias circuit, which there was no bias circuit before in the original power supply because the original power amplifier was self-biased. That had a large emitter resistor that was bypassed by a capacitor. Emitter resistor, I meant to say cathode resistor. I'm thinking solid state here. It had a large cathode resistor that was bypassed by a capacitor. The new output stage does not have this. It is grid biased, so there is a negative bias supply built into this power supply. And you can see it coming off of the right-hand side of the bridge rectifier, going through a resistive divider, then going through filter caps and resistors and variable resistors. The variable resistors will be what you'll use to set your bias. Now, I did mention, I think in a community post, that one of the ideas that I had was to have a switch that would allow the VU meters to also act as bias indicators, so that you do not have to hook up any kind of external metering to the amplifier in order to set the bias. Simply put, you would install your output tubes, turn the amplifier on, let it warm up for about 5 minutes, flip the switch on the meters so that they indicate bias instead of audio level, and then adjust the two bias potentiometers, one for each tube, until the appropriate meter reads exactly 0. And then you're properly biased and you're done. You can flip the switch back down and now the meters indicate audio. This brings us to the next schematic that I want to show you. At the top, you see the original circuit that was used to drive the meters as VU meters. You have a voltage doubler that full wave rectifies the audio coming out of the output stage and feeds it through a resistor to the meter. Now, it is proper to use a voltage doubler because it's an easy way to get full wave rectification so that you can see voltage peaks from both positive and negative spikes. However, they've got the voltage doubler connected directly across the speaker terminals. So that 10 microfarad capacitor, which is in series with a diode, is directly across the output stage. This is not a good idea in a power amplifier that has a very high output impedance, as single-ended tube amps do. It's going to cause second harmonic distortion. It should not be done like that. So I have modified that circuit to have a 100 ohm isolation resistor between the voltage doubler and the output stage, and then I'll put another resistor in to set the meter sensitivity as I like it. This will reduce the possibility of the meter circuit causing distortion. So here I'm going to show you a picture of a little bit of the work that I've done inside the amplifier. I haven't really had time to do any actual serious work inside the amp because I'm busy fixing other people's gear. But I have wired the filament circuits the way that I want them. I mentioned in a community post that I was thinking about putting in a switch to allow it to use either 12 SN7s or 6 SN7s, but I recently acquired a full set of tubes for this amplifier from a friend of mine named Jim McMillan. Jim is a local guy here in Chattanooga who sells very good quality used, and I don't know if he has new tubes or not. I think he's got both new old stock and used tubes that are tested. He has a very high quality tube tester called a TV7. I know he has it because I have installed 2 new tube sockets in it for him. And I want to thank Jim for helping me out with these tubes. And you'll find his phone number down in the description. If you need any tubes for your audio gear, give Jim a holler. I'm sure he'll be happy to help you out. And for the record, I am not being paid to plug Jim. I'm mentioning him because I appreciate his assistance. So there you go. That's enough for right now. I will say thank you and so long, and I'll talk to you later. Bye-bye.